question is, what is this flow rate in meters cubed per hour? And the choices are A, B, C, D, E. And I'll say 5.0 times 10 to the third meters cubed over hour. 18 meters cubed over hour. 1.8 times 10 to the fifth meters cubed per hour. Or 1.8 times 10 to the third meters cubed per hour. Or 5.0 meters cubed per hour. Okay? And I will, so how many of you have your clickers already? All right, so we're going to do the clickers, but I'll give you another day before it starts counting as extra credit. I just want to get everybody enough warning that we're going to do clickers. So tomorrow we're going to have it worth extra credit. Today we're just going to use the clickers so that we get the used to that, doing it, okay? Is that all right with everybody? Okay, so let me do that. So the base frequency code is AA, so if you don't have it already, just put in AA. Press and hold power button down for 2 seconds, and press AA, okay? And then we are going to see what people say. While you're doing that, I'm just going to go in the back and see how well you can read this, whether I need to make my writing a little bit larger now. That's readable, but I can write a bit larger. Okay. I'll write a bit larger. Oops. Careful about that. Okay. So you had a chance to click in. So how many seconds in an hour, by the way? Yeah, that's useful to know. 60 seconds in a minute, 60 minutes in an hour. Sorry, 60 minutes, yeah, that's right. 60 minutes in an hour, so 3,600 seconds in an hour. Okay. So let's, all right. If you haven't had a chance to click in, click in. And let's see what people have said. Okay, so as I said, this is not counting for anything. We'll do it for extra credit starting tomorrow. But let's see what people have said. Okay. All right. We've got lots of B's and C's, a few D's and a few A's and E's. So let's take a look. So remember, as Dr. Kohler presented, or yeah, he would have presented that material, that, you know what, just a second, this thing is way too high. Okay, that's way too low. Okay, I'll just do it like this. Okay, so we have 5.0 times 10 to the third centimeters cubed divided by seconds. If I'm going to use the substitution method, I would say, okay, I have the centimeters that's being cubed, so think of that as something raised to the third power. 1 centimeter is equal to how many meters? Point what? Yeah, 0.01 or 1/100th of a meter. So 0.1 meters. And then a second, I want to convert that into hours. So first of all, so we have 1 hour is equal to 3,600 seconds. But I want to go the other way, so 1 second is 1 over 3,600 hours. So now what I will do is I will substitute. I'll substitute, and then I get 5.0 times 10 to the third, and then I have 0.01 meters. And remember, that's raised to the third power, so that's why I have this third power there. And then I divide by, and I'm replacing this 1 second by 1 over 3,600 hours. Does that make sense, everybody? Okay? Now, if you're going to make a mistake on this problem, it would probably be forgetting that this 0.01 has to be raised to the third power, because you notice this centimeters is raised to the third power, so when you substitute 0.01 meters, it has to be raised to the third power. Does everybody get that? Okay. If you don't get that, then you're going to screw up these problems whenever you have things raised to powers. All right, then you just have to punch these into the calculator. You end up getting 18 meters cubed per hour. Right? And the answer was B, I believe. Any questions about that? Everybody got that? Okay. All right, let's go on. Let's cover some new material now. Oops. This will be written here already. Okay, we're going to talk about motion in one dimension. The reason we're going to talk about motion in one dimension is because motion in one dimension is easier than motion in 2 dimensions or 3 dimensions or whatever number of dimensions. Okay? So everything's moving in a straight line. Okay, so let's consider this thing called a motion diagram. And what I mean by motion diagram, your book does a lot of these pictures. They're basically snapshots of an object that's moving, so snapshots. At equally spaced time intervals. All right? You know, one way to think of it is if you had a strobe camera, you know, like a camera that blinks like this with the fixed interval, and you see a ball moving, you would see, here's the ball, here's the ball, here's the ball, here's the ball, okay? That's what a motion diagram is. That's basically all it is. So if I'm talking about motion in one dimension, and I look at this motion diagram, let's say the ball is moving along the x-axis, so here's the positive x direction, okay? And let's say this is the y direction, but because I have motion in only one dimension, say the ball is here, then it moves to there, then it moves to there, okay? So the way I've drawn it here for this motion diagram for this ball, does it look like the ball is moving to you? Is it moving? Yeah, well, okay, that's what the motion diagram is supposed to indicate. The fact that I'm not drawing the ball at the same place every time it's moving, okay? And the fact that the separation between these balls, as far as I can draw, to the best of my drawing ability, is about the same, right? And so I've drawn it in the case where how fast it's going is about the same at all times. Does that make sense? Okay? If it was getting faster, then these intervals would get bigger as it went along. Okay, so now notice one thing I did here was I labeled the direction of the motion x, and that's convenient. So it's convenient to call the direction of motion as the x-axis. If it was not in that direction, it was some other direction, so it was not these nice arrows. So suppose it was over there, then we just say my x-axis, my plus x-axis direction is in that direction. If it was over there, we just say, or let's say there, then my x-axis would be in that direction. Okay? That's all it is. And because it's only in one dimension, we can essentially ignore the y and the z. We just don't even think about them. Now, the next thing I'll talk about is a vector. A vector. Actually, you guys have learned about vectors before, I know. So somebody give me a definition of a vector. Yeah. Yeah, something with magnitude and direction. Okay, so a vector is a quantity with magnitude and direction. So if you want to draw it as a picture, it's just basically an arrow. It has a starting point, it has an end point, and just a little arrow. Okay? And if you're drawing it as a variable, as a notation, if I call this vector A, then we like to put a little arrow hat on top of it to indicate it's a vector. Now, this arrow hat is how we write vectors, but if we're in one dimension, things get a little bit easier. So things get easier in one dimension because directions are rather simple in one dimension. So let's consider an example, something that's called displacement. Okay? Let's talk about displacement. So displacement. Now, in general, we call the displacement, in general, we will call it delta R like this, in general. But for the one-dimensional case, in one dimension, it's a little bit easier. Okay? By the way, this symbol delta is something we'll use over and over again. Delta means the change in something. Delta t is the change in the time, or the time interval. Delta R will be the change in R, where R will indicate the position. But let's consider the displacement in one dimension. And so I'll have a number line here. And let's say I have, this is my initial. That's the initial. Here's my final position. But then the change in the position is the final minus the initial. So we say delta x, the displacement, will be x final minus x initial. Any questions about this? Does that make sense? Okay. Now, as I said, vector can, something with magnitude direction. However, if something's along one dimension, the directions can only be in one of two directions. It can either be positive or it can be negative. Okay? So in the case of one-dimensional motion, we don't really need the full machinery of vectors. We can just simply say whether the direction is positive or negative. In one dimension, the direction is either positive plus x or negative minus x. By the way, if I write and you see me talking and you don't see me writing on the screen here, it's because I've gone off the edge. Just don't even raise your hand. Just yell at me say something like, hey, you're off the screen, okay? Now, so if I have, let's say, a number line, again, where I've labeled the x positions, let's say this is 0 meters, here's 10 meters, here's 20 meters, let's say here's 30 meters, 40 meters. Let's say I go from, let's say from here to there. I start off at 10, I end up at 20. I'm going to try to draw these a little bit bigger than that for people in the back. Sorry, that was a little too small. So I start at 10, end up at 20. Then the delta x in this case will be plus 10 meters. Okay? If I'll make the number line a little bit bigger this time. $30 meters, 40 meters. Suppose I start over here and I go back like this. I start off at 40, end up at 10. I do final minus initial, 10 minus 40, I get negative 30. And so in this case, the displacement x is equal to negative 30 meters. Is everybody okay with that? All right. Okay, so now, in particular, we can label our motion diagrams using these displacements. So I can draw a motion diagram. And let's say I have a ball here, and then at the next time interval, it's over here, and then at the next time interval, let's say it's further along. So I can say, here is my displacement for the first time interval, delta r1, and then for the second time interval, I have a delta r2, and then so on, and I can go on from there. Everybody follow me? By the way, my goal when I'm lecturing is that you guys can follow what I say in real time. I know there are some professors who are very deep, who tell you things, and then you go home, you think about it for a couple hours, and you figure out what he or she said. I'm not trying to be like that. So if you don't understand what I'm saying, it's because I didn't say it very well. Just ask me questions. Okay? All right, now, so let's now consider a time interval. Let's call it delta t. Delta t. That's just the final time minus the initial time. And let's say at the beginning of the interval, a particle is at x initial for the beginning, and at the end, the particle is at x final. Okay, then we know the displacement. The displacement is delta x is equal to x final minus x initial. The new thing I'm going to define is something called the average velocity. So the average velocity is, and I'm going to use the notation v sub avg, avg for average, and this will be delta x over delta t. Okay, so this I just said was the displacement. Okay, and delta t is the time interval. Questions about this? Average velocity, delta x over delta t. We can also define something called the instantaneous velocity. And the instantaneous velocity is the average velocity, but as we take delta t to 0. So we take an interval of time that gets smaller and smaller and smaller. Okay? So we take what's called the limit. So if we have the instantaneous velocity, v, this will be the limit. So everybody's okay with this notation, limit? You put something goes to 0 or something underneath, right? All this calculus notation. Okay, so limit as delta t goes to 0, delta x over delta t. All right, so we're going to take smaller time intervals and then get the ratio of delta x over delta t. And this is what we call dx dt, the time derivative. Right? From calculus. The limit of delta x over delta t, this is what we call dx over dt, which is the time derivative of the position. So it's the time derivative. Let me write that out in words. So the instantaneous velocity is the time derivative of the position. delta x, the change in the position, is what we call the displacement. Okay, any questions about this? Now, let's suppose we make a plot of the position versus time. Plot of position versus time. Okay, so whenever you say something versus something, the first thing you say will be on the vertical axis, and the second thing you say will be on the horizontal axis. So I'll have x here, that's my position, and t here will be time. Okay, I'm just going to draw a nice smooth curve, and let's say we have something like this. That's going to be the position versus time. All right, now let's pick a little time interval. Let's suppose, and I'm going to make it kind of small, but not too small so you can't see anything. But let's say we make a little triangle here, okay? And so this will be delta t, the time interval, and this little thing here will be the delta x, which is kind of hard to see. And so the instantaneous velocity is the limit as delta t goes to 0 of delta x over delta t, or what we call dx dt, the time derivative. And so that is giving me the rise over the run. You know, if you have this little slope sort of thing, right? Rise is how high it goes up divided by how far it runs horizontally. That's the slope of the curve. So that's the slope of the curve. But that's something you should remember from calculus class, right? The slope of the curve is the same thing as the derivative of the function. Everybody remember that? Okay. Okay. Any questions about this? Any questions? Yes, questions. Okay, so it's a ratio. It's the delta t over delta. So sorry, the delta x over delta. That's the ratio of the two. Okay, now if we have a general time interval, or a general time interval, not necessarily small, delta t, we get the average velocity remember we call that v sub avg. So in that case, we take a larger interval of time. Okay, say this is my x versus t. Let's take an interval, let's say from this time, t initial, to this time, t final. Okay, then this, let me draw a horizontal little thing here. Then this is my delta t, the difference between t final and t initial. And then I will take the points here. These will be my x initial, and my x final. Okay? And on this side of this right triangle will be delta x. And so then the ratio of those will give me the slope of the triangle, where the triangle intersects these 2 points here. And so then v average will be delta x over delta t. It's the same thing I had over here. The only, oh, you can't see that, as I had over here. The only difference is in this case it's a big triangle, whereas above it was an infinitesimally small triangle. Okay. Everybody's good on that? All right. Now, next thing I want to say about velocity is the units and the System International unit, the metric unit, if you want to call it that, the SI unit for velocity is, yes, what do you think it is? Yeah, meters per second. It's meters over second. Since we're saying it's delta x over delta t, to get units right, meters per delta x over t, seconds per time. Okay, that is velocity. Let's now talk about acceleration. Okay. let's define the average acceleration a sub avg is defined as a sub avg is equal to delta v, the change in the instantaneous velocity, over delta t. So this is the change in instantaneous velocity. And this is the usual, the time interval. So you have a time interval, the velocity changes. Okay? That's what the acceleration means. That when something accelerates, the velocity is changing with time. So you take your delta v over delta t, and that gives the average velocity. While we're at this, we can also talk about the instantaneous acceleration. Instantaneous acceleration is defined as just plain old a is equal to the limit as delta t goes to 0 of delta v over delta t. And this guy is going to be the time derivative of the velocity, the instantaneous velocity. Okay. Any questions about this? So you good? Okay, so I should mention, because instantaneous is kind of a long word to write down and to say every time, there's sort of a default notation. So the default is velocity. If we just say velocity, we means instantaneous velocity, unless otherwise indicated. Okay? If you say average velocity, obviously you mean average velocity. Okay? But if you just say velocity, it's implied you mean instantaneous velocity. And the default for acceleration is that acceleration means instantaneous acceleration. Okay, questions about this? Everybody's following so far? Not too fast? Maybe a little too slow, but at least not too fast? Okay. All right. Now let's go on. If we plot, let's now make another plot. Let's plot velocity versus time. Plot of velocity. Remember, that means instantaneous velocity versus time. Okay, and let's do that. Here's my velocity. And here's my time. And just for fun, let's make a different curve. Let's make it more squiggly like that. Okay, and now if I have, let's say, a little time interval here, here's my delta t again. And let's say, here's my little triangle. The little triangle, that's my delta v. Then I can write down the instantaneous acceleration. It's the limit of delta t going to 0 of the ratio d delta v over delta t, or just the time derivative of v. And so we have that the instantaneous acceleration for short, acceleration is the slope of the velocity versus time curve. Okay? Any questions? Good? All right, let's get some intuitive feeling for this, though, okay? Let's talk about my motion right now relative to the room. If you were to describe how fast I'm moving right now, what would you say? Not very well. Okay. So, is my velocity going to be, what would my velocity be? 0. Okay. Now, what would my acceleration be? Okay, because my velocity remains 0, it's not changing, so the acceleration is also 0. Okay. Now suppose don't start the clock yet. Now, I started here and I'm walking like this. My velocity is obviously non-zero, right? Okay, but how about my acceleration? Let's stop the clock at that point. Okay, what was my acceleration during that period of time? Yeah, you notice that even though the velocity is non-zero, it wasn't changing. I was as much as possible trying to keep it the same. So because my velocity is not changing with time, delta v is 0. Okay? And so delta v or delta t is also 0. All right, so we can make these links. Actually, I did want to tell you about the units for acceleration. I didn't give you that, so let me just write that down first before I tell you these links. So the SI unit for acceleration. Okay, anybody can guess what that unit might be? Meters per second squared. Okay, that's because velocity was meters per second. We do another over delta t kind of thing, and we get another second in the denominator. Okay. So now let's describe some of these motion diagrams. Let's take a snapshot of these. Let's say we have a motion diagram like this. Okay, and let's say, so let's just take it as a little particle, and we have delta R1, okay, and then let's suppose it goes to here. Maybe I went a little too far with that, but okay, now I have to go really far. This delta R3, okay? All right, so if I'm looking at this motion diagram and I'm trying to figure out what my delta v's look like, what my average v's look, average velocity, average velocity looks like at these various time intervals. So let's suppose I want to know the velocity in this time interval. Okay, let's say it's this much. The thing is, I don't really know exactly how big the average velocity is because I didn't tell you what delta t is. This is just making sketches. Okay, I'm just drawing sketches. Let's say that the v1 was like this. Okay, something like this. Then is it clear that when I draw the v2, it should be scaled up to be bigger than the v1? Does that make sense? Okay. Why is that? Because when I calculate the average velocity, I'm being a little lazy. I'm not putting ABGs on these little things because that's kind of annoying. The average velocity would be delta R over delta T. And it will be the same delta T for these motion diagrams, right? That's what the motion diagrams are for the same time intervals between the snapshots. So if this is proportional to that guy, the same proportionality has to exist between this velocity and this displacement. Does that make sense? Okay. And then this guy has to be proportionally bigger as well for the velocity for the average velocity for this interval. Everybody's good on that? Qualitatively, and it's just drawing diagrams. I'm not calculating anything, but that's what it should look like. So now if I want to know the acceleration, if I want to go one step further, what does the acceleration look like? Well, it looks like the velocity it's pointing to the right, and it's getting bigger, right? Okay. So which way is the vector, which way is the acceleration pointing? Pointing that way. Okay. So if you want to think about it, let's say this is the positive direction, then the velocities are all positive, but the numbers for the velocities get bigger. So the acceleration will be a positive number, meaning it's going in a positive direction. Okay. So in this case, let's say it's the same acceleration because I can't draw well enough to distinguish something other than that. Then the acceleration would look like this, okay? I would actually need more information over here, but let's say it just keeps doing what it was doing. Is everybody okay with that? Let's suppose I have a motion diagram that looks more like this. Okay, I have delta R1, delta R2, delta R3. And if I get the velocities on for these intervals, then let's say this guy is V1, Okay, then this one will be smaller, v2. This guy would be even smaller, v3. Does that make sense to everybody? Okay. Now in this case, if I'm talking about the acceleration, which way would the acceleration point? Which way would it point this time? Yeah, it points to the left. Okay, because the velocities are all going to the right, but they're getting smaller. So there's a decrease in the size of the velocity. So you can think of it, if you want to think of this as the positive x direction, you have positive numbers that are getting smaller. So the acceleration must be a negative number, meaning that it's pointing in the negative x direction. Everybody got that? The negative sign would tell you it's pointing in the negative x direction. Okay, so the acceleration would be pointing like this, a1, a2, a3. And I already covered the case where we had, let me just do it. I did this with walking, but let's just cover the last case. So if we have the motion diagram for completeness, if we have evenly spaced, so let's say evenly spaced delta R1, delta R2, delta R3, okay, then these velocities would be the same, v1, v2, v3, right? Because they're all the same size for the delta r's, so the v's will be delta r over delta t, they'll all be the same size. And the acceleration in this case, what was the acceleration? 0. So a1 equals 0, a2 is equal to 0, a3 is equal to 0 because the velocity doesn't change. Questions about this? Okay. At this point, let's try another clicker question. So let's take out clickers. Example. Let's say a person walks home. No, starts from home. Starts from home. Walks 2.0 kilometers east in 1 hour. She then turns around and walks 1.0 kilometers west in 1 hour. What is her average velocity? Okay. In the 2 hour, I should say, in the 2 hour period. In the 2 hour period. Okay, let me give you some choices. Okay, 2.0 kilometers per hour east, 3.0 kilometers per hour east, 1.0 kilometers per hour west, 1.0 kilometers per hour east, 0.50 kilometers per hour east. Okay, and I will open up the clicker response. Okay. Go ahead and make your choice. All right. Everybody had a chance to reply? All right. Let's see what people have said. Let's stop it now. Okay, we have D's and E's. E's more. Majority of E's. Let's see how it goes. Okay, so the suggested thing to do is to draw a diagram. So first of all, let's say this is going to be east. You want, it's the positive x direction, let's say, is that way. But then first of all, the person moves 2.0 kilometers east. And then the person turns around and goes back halfway, 1.0 kilometers. And the interval is going to be from the very beginning to the very end. And so we want to know what is the delta x for the entire thing. And that's just basically what is the displacement from here to there. Okay, from this initial to that final. So that will be 2 kilometers plus the minus 1, okay, or 2 minus 1. And so that's 1.0 kilometers. And the delta t is, well, it's 2 hours. And so we can get the V average is going to be then 1 kilometer over 2.0 hours, and that's 0.50 kilometers per hour. Okay. Questions about this? Everybody's good? Okay, we do have a few minutes left, so if you have to go to your other classes, I realize everybody has their own constraints you can take off, but I want to just quickly do a math review so you guys are prepared for all of the vector stuff we're gonna do very shortly. So let me just I was hoping this would be covered on the first day of classes, but let me just show you the notes I had from the first day. So make sure this is in your memory bank somewhere, okay? So this is an angle review. So if we have, let me just do the refocusing here. Okay, so when we have two straight lines that meet, then the angles that are opposite to each other are equal. These are what are called vertical angles. You guys remember that from high school geometry or whatever? Okay. Now, when two angles share a straight line like this, they're called supplementary angles. The name isn't that important, but they add up to 180 degrees. Okay. Now, the sum of the interior angles of a triangle is 180 degrees. Remember that? Okay. And then if we have a right triangle, meaning one of the sides is 90 degrees, the sum of the other two must be 90 degrees. So alpha plus beta must be 90. And then we say alpha is 90 minus beta. They're complementary angles. If we can take angles in degrees or in radians, so 2 pi radians is a full circle or 360 degrees. Pi radians is 180 degrees. Pi over 2 is 90 degrees. And then the lightning fast trigonometry review. We have a right triangle. We have an angle of theta. The opposite is A. The adjacent side is B. The hypotenuse is C. Then the sine of the angle is the opposite over the hypotenuse. That's A over C. The cosine of the angle is the adjacent side over the hypotenuse. That's B over C. And the tangent is the opposite over the adjacent, which is A over B. And the Pythagorean theorem is a squared plus b squared is equal to c squared. And so c is equal to the square root of a squared plus b squared. Okay. I'll see you guys tomorrow.